Okay, good afternoon. So I wanted to, your GSI should have said this, but I just want to say a couple things about the midterm before I get to other stuff. And by the way, I'm sick, so I'm sucking on a cough drop, so, you know, I don't know, don't get too close. I'll try not to breathe or cough on anything. Okay, so I wanted to say about the midterm. You should have the summary statistics, but I'll just put them on the board real quick because I want to talk just a little bit about them. So the average was 74.6. SD was 18. And that's, you know, it's always nice to know the average and the SD. For the midterm, I think it's probably more useful to know the percentiles, in particular these percentiles. The 10th is 48. The 50th is 80. And the 80th is 90. So it turned out just, oh yeah, so if you got 90 or more on the midterm, some kind of an A, between 80 and 90, some kind of a B, between 48 and 80, some kind of a C, and below 48, some kind of D or F. So I want to say a little bit about that because I think there's a tendency to kind of focus on the letter grade, but really you got some number of points on the midterm. Those points are going to be weighted and added to other stuff, you know, midterm and quiz and homework and the final, and you get some total number of points. And that's really what's relevant, is that the total number of points at the end, that's what I'm going to calculate the percentiles for, assign the grades based on that. So it's not like, you know, it's not like if half your grade is an A and half of your grade is a C, then you necessarily get a B. So it depends on what the actual points are. But this, I wanted to give you this because it does give you sort of roughly what you're doing in progress on the midterm. In a way, like if you got an 89 or something and you're disappointed because you almost got an A or something like that, it's 1 point, right? So you're being 1 point away from an A is not a big deal as far as overcoming that, you know, on everything else in the class to give you a little bit more to get an A. So, you know, if you're kind of close to the boundaries, you're close to the boundaries. Okay, does anyone have any questions or anything about that stuff? Okay, so, you know, if you have individual questions you want to talk to me about, feel free. Otherwise, hopefully, if you had any complaints or, I don't know, felt like your midterm wasn't graded right, hopefully you gave that to your midterm, to your GSI already, and we're going to go over those. Thursday, you'll get them back after spring break, I hope. Okay? Okay. So I want to finish up chapter 17 today and get into chapter 18. Any other questions about anything else? Yeah. If you didn't give the midterm to your GSI, why don't you talk to me after, either during the break or after lecture? Okay. Any other questions? Okay. All right, so first thing I want to do is just sort of, I wrote this on the board last time, but I kind of think it's nice to emphasize the similarity between what we're doing now and what we did in the very beginning of the class, chapters 3, 4, and 5, and what's going on now in chapters 17 and 18. So these chapters, chapter 3, 4, and 5, they basically deal with data somehow. You have some lists of numbers, data, and for the data or for the list of numbers, we can do some things. We can find a histogram, which is just, you know, a picture of the data. We can find summary statistics like average and SD. And we can do some stuff with the normal curve. So roughly, this is what's in chapters 3, 4, 5. Okay. Chapter 3 is histograms. Chapter 4 is average and SD. Chapter 5 is using the normal curve with data. Now, chapter 17 and 18 follow a similar pattern, but we're talking about a different situation. you can think of this as having to do with chance processes as a sort of general thing. And in particular, we're talking about taking the sum of draws from some box model. So chapter 16 tells us how to make box models for chance processes. And then chapter 17 and 18 deal with sort of why we do that and what we use it for. Okay? So if you're talking about sum of draws from a box, we can talk about what are called probability histograms. I haven't yet, but that's the subject of chapter 18. I'll talk about that before the end of the lecture. And we can talk about expected value and standard error. This is chapter 17, and I've already done that. And then we can talk about the normal curve also. And I'll refer to this as normal approximation. This is also in chapter 18. And I think I'll get to that a little bit today, but I won't finish. I think I'll have to finish on Thursday. But again, I want to sort of emphasize this relationship. There's pictures, and we have kind of a corresponding picture here. And you think about what's happening here. What is this a picture of? This is a picture of sort of what could happen. This is dealing with some chance process or sum of draws. If you imagine like flipping a coin 100 times and counting the number of heads, well, you expect to get around 50. So that 50 tells you the expected value. I calculated the standard error for that situation on last Thursday. Standard error is 5. So we expect about, in 100 coin tosses, we expect about 50 heads, give or take about 5. Okay? And that sounds very similar to what we talked about with average and SD at the beginning of the class, talking about like average is sort of the center, kind of a typical maybe height for someone, and SD tells you about how far off you might be from that typical height. And we have the same idea here. And if you know the average and the SD, and you know the histogram looks like the normal curve, you can do a bunch of stuff in chapter 5. So there's a similar structure here. If you know the expected value and standard error, you can calculate it based on your box model. You know the probability histogram looks like the normal curve, you can do normal approximation. So we're essentially saying that kind of what could happen looks like the normal curve, right? We don't necessarily have any data. We don't have to actually toss any coins to say that if we did toss 100 coins, we expect to get about 50 heads, give or take 5. So we don't have to actually toss any coins to make what's called a probability histogram. But we need to know something about probability. Okay, so I'll get into this, in a little bit. I haven't quite finished up chapter 17, but I wanted to kind of open things by getting your mindset in this big picture idea that there are a lot of similarities between what we're doing now and what we did before. It's just a different context. Rather than talking about concrete lists of numbers where we actually know what the numbers are, this is a little bit more abstract. We're imagining tossing a coin 100 times and thinking about what could happen. Expect about 50 heads, give or take 5. Okay? But you don't have to actually toss any coins to do that. You just have to know something about probability, box models, that kind of stuff. Okay? Any questions about this? Okay, so I wanted to compare, contrast, and I'll refer back to that a little bit as we go along. Okay, so to finish up chapter 17, there are a couple loose ends I wanted to do. I like to sort of skip over, let me talk about chapter 17 bit by bit. Chapter 17 has 5 sections. The first section talks about expected value. The second section talks about standard error. The third section talks about the normal curve in a very kind of loose, intuitive way. And I've talked about it at about that level. I'm not going to say anything more specific about 17. I like to sort of wait until chapter 18 to do it in detail. The fourth section of chapter 17 talks about a shortcut for calculating the standard deviation. And this shortcut is not that exciting, okay? It's not, if you see the SD shortcut, maybe you're a little bit excited that, oh, this is some fast way of calculating standard deviations. Calculating standard deviations is kind of a drag, so maybe this is a good, cool thing. It's shorter, but it only works for one situation, this shortcut, and it works when this is for, I'll describe it this way, for boxes with only 2 kinds of numbers. Really, it works for any list of numbers that has only 2 kinds of numbers. Okay? And if you think about, so essentially what I mean is that the tickets in the box are either one value or they're another value. And the calculation of the SD goes like this. You take the big number out of the 2, subtract the smaller number, and then multiply by the square root of the fraction of the numbers that are big times the fraction small. So part of the reason I'm saying it's not really that exciting is that it only works in this situation with only 2 kinds of numbers. In that situation, calculating the standard deviation is actually not that bad anyway. So it doesn't, this shortcut doesn't help you if you have some messy, complicated box. But it is faster. So, there it is. So a real quick example of this. I'll do it for coin tosses. Suppose we have this situation that I mentioned. So this is like 100 coin tosses, counting the number of heads. The average of the box I've done before, just 1 plus 0 over 2 is a half. And we can use this shortcut to calculate the SD. So the way I calculated the SD before is just by the usual SD formulas. Either one. You could either do it by RMS of the deviations from average, or you could do this kind of summation formula, square root of the average of the squared values minus the square of the average. I'll do it now using this, just to illustrate what's going on. 2 kinds of numbers. The 1 is the big one. The 0 is the small one. So we go 1 minus 0 out in front. And then multiply by the square root of fraction big. Half of them are 1s, and half of them are 0s. So 1 times square root of a half is a half. OK, so that makes life just a little bit faster than using either summation formula or RMS, the deviations from average. OK? Questions on that? OK. So, yeah. Question?
So that would still work if you have something like, if you have something 1, 1, 1, 1.
1, 1, 1, 1, 10 still works, yeah. So then that box, so 4 1s and a 10, you'd go 10 minus 1, big minus small. Fraction of 10s is 1/5, fraction of 1s is 4/5. Okay, so just kind of crank through, yeah. The SD here, I'm talking about the SD of the box itself, average of the box, SD of the box. If you want to continue to calculate expected value and standard error, expected value for the sum of 100 draws from that box, or you could think of it as expected value of the number of heads, is the number of draws, 100, times the average of the box, 1/2, that's 50. The standard error for the sum of the draws, or SE sum, I sometimes write it, square root of the number of draws times the SD of the box, 1/2. Square root of 100 is 10 times a half is 5. Okay? So I did that calculation at some point, I think last Thursday. But yeah, these depend on the number of draws, right? So how many, so this is kind of these are kind of characteristics of the coin tosses themselves, regardless of how many times you toss the coin. And then if you actually want to think about doing something like tossing the coin 100 times, then get expected value standard error. Okay, good. Was there another? Yeah. So she's suggesting that maybe this should always be 1/2, 1/2. You don't have to have one of each. So someone was thinking about this hypothetical example. Maybe I'll just write it down. What if you have, well, actually, I'll do the example I was going to do, which is, suppose we play roulette, slightly more complicated example. You don't have to know anything about roulette. If I ever want to give you problems on roulette, I'll explain it. It's discussed in some detail in the book. And suppose I bet $1 on red. And I'll just make it 100 bets. OK, so the way that the roulette wheel works is that there are 38 slots. I'm not going to try to draw them all. Oh, 5. Okay, rough, you know. What happens is the roulette wheel, you spin the roulette wheel and you throw a ball in there and the ball kind of spins and bounces around and it ends up landing in one of these 38 slots. And of those 38 slots, 18 are red, 18 are black, and there are two that are green. They're also numbered. Okay, they're also numbered 1 through 36. These are numbered 1 through 36, and these are 0 and 00. For this problem, you don't need to know about the numbers. You just care about the color. So if you bet $1 on red, if red comes up, you win $1. So I should say it this way. If the ball lands on red, or lands in a red slot, win $1. Otherwise, lose $1. Okay. So maybe I'll just, as an aside, the way the book describes this is that if the ball lands in a red slot, the casino gives you your $1 back plus another $1. Okay. So I'm not quite sure like why the book words it that particular way. That means you win $1, right? So like I go and I bet, I put $1 on the table, and I wait and I see if red comes up. If they give me my $1 back, that's not money that I'm winning, right? That's like, okay, I'm breaking even, but then they give me $1, so I win $1. Okay, so yeah, so I'm not quite sure why they describe it that way, but anyway, otherwise you lose your $1, you walk away, right? Okay, so anyway, that's what's happening. Now let's think about making a box model for this situation. When we make a box model, what we want to think about is what can happen. Like, so first of all, what is the quantity we're interested in? When I gave you instructions on how to make a box model, I said, first thing to do is think about, well, what kinds of numbers are going to go in the box? And I said, in thinking about that, you kind of want to think about what could happen to the quantity of interest on each draw or each play. So what's the quantity that I'm interested in? Like in English, what do I care about? Someone said color, someone said chance I win on red, someone else said amount of money you win. Yeah? 18 and 20. Well, I don't want to know what the box is yet. I want you to think about this a little bit intuitively, like what is it I care about? What I care about is how much money I win or lose, okay? So that's sort of the quantity I'm interested in. Each time I play, what can happen to my money numerically? Yeah, it either goes up by 1 or it goes down by 1, right? Either I win, ball lands in a red slot, and then I win $1, or my money goes down by 1, I lose $1, okay? So when you think just purely about what numbers are going to go on the tickets, I want to put a -1 and a +1. So this is -$1 and +$1. Oops, let me get. So if we're writing this down, leave a little space because I want to say how many of each of these. Okay, so first step is to think what numbers go on the tickets. Second step in making a box model is how many of each. And you need to make sure the probabilities come out right. So in the coin tosses, equally likely, heads and tails. Okay? In this case, well, you can think of what's the chance I win, or what number should I put here? 18. There are 18 ways for me to win $1, and there are 20 ways for me to lose $1. Okay? So if you want to sort of think about it, there are a total of 38. 20 plus 18 is 38. And I have an 18 out of 38 chance of winning $1, 20 out of 38 chance that I lose $1. Okay, so that sort of works, comes out right. The chances are right. Okay, so then once you do that, then number of draws, 100. Okay, any questions about that? Okay, so then from that box, I can calculate the average. Once you get your box model, everything's sort of automatic in a way. You need your average of the box, SD of the box, expected value, standard error. So 38 tickets, 20 of them are marked -1. So this is like -1, -1, -1, 20 times. And then 18 positive ones plus 1, 1, 1, 1, 1, 1, 18 times. Divide by 38. And that comes out to be minus 0.526, 0.0526. And let me just get the expected value, I guess, first. This is number of draws times the average. Comes out to be minus 5.26. Okay, so interpretation of that minus 5.26 is that if I went and I gambled, played 100 times at roulette, betting $1 every time, I should expect to lose about $5.26 on average, right? So if we took a field trip and everyone did this, sort of long run average you'd expect for people to have, right? Now, presumably, people would not play if they always just lost $5.26. It'd be sort of a boring game if you just knew going in, okay, if I play 100 times, I'm going to lose $5.26. So what makes it sort of fun or exciting is the chance you might actually win money. So you'd hope at least that the standard error would be big enough that sometimes you'd win money. So let's calculate that. Standard deviation of this box, I'll use this little shortcut formula, 1 minus negative 1. So the big thing in the box is a 1. The smaller value is a negative 1. And then, multiply by the square root of fraction big times fraction small. So there are 18 out of 38 big ones and 20 out of 38 small ones. And this is very close. This comes out to be very close to 1. Okay, we have a 1 minus negative 1 out in front. That's 2. And then if you calculate this, it's very, very close to a half. So we get about 1 for the standard deviation, and the standard error, square root of the number of draws times the SD of the box is 10. Okay? So, if we did this, gamble 100 times, we expect to lose about $5.26, give or take about $10. Right? So it's totally reasonable that we might get an SE above average, or a couple SEs above average, even above the expected value. So we might win some money. We might also, lose more. We might also end up an SE or two below. So, there's some chance we win, but certainly the game's against you. Okay? Questions on that? Yeah. Okay. Sorry, I got a little scrunched at the end there. I was trying to fit it all on one board. So I'll talk through this again. The SD is 1 minus negative 1. This is the big minus the small. Square root of fraction big is 18 out of 38. Fraction small is 20 out of 38. That's 1. Standard error is square root of 100 times the SD. 1 gives us 10. OK. Other questions, comments? OK. So let's see. OK, so I want to finish up. So this is the fourth section of Chapter 17 deals with this SD shortcut. The last section talks about classifying and counting, and we've done that. So the idea of classifying and counting is that if you are trying to count the number of times something happens, you can think of your box as containing 1s for the things you're counting and 0s for everything else. So make a box with tickets marked 1, 1s for what you're counting. And tickets marked 0 for everything else. Like I said, we've already done this. We've already done this for coin tosses. This box for counting the number of heads in 100 coin tosses, the 1s represent the things we're counting, the heads. The 0s represent everything else, the tails. Another example, Just do real quick. Suppose I roll a fair die 100 times. And I want to count the number of sixes. So last time I made a box model for just die rolls, right? 1, 2, 3, 4, 5, 6. If I want to take the sum of the actual die rolls, that's what I would use. For counting the number of sixes, I'm doing this. I'm classifying the sixes as the things that I want to count, and everything else is a 0. So that's going to look like this. Another way to think about this 0 and 1 thing is that what could happen to the number of sixes on each die roll? Either the number of sixes goes up by 1 if I roll a 6, or it stays the same if I don't roll a 6. So that's another way to think about why I have a 1 and a 0 here. Then I want to think about how many of each. Well, this represents a 6, so there's 1 of those and 5 non-6s. So again, the chances need to come out right. You want a 1 out of 6 chance of getting a 6. And then 100 draws. Okay, so I'll do the math really quick. So we have the average of this box. Some of these numbers in the box is 1 divided by 6. And SD of the box. Again, I'll use this shortcut. We have the big numbers of 1, small numbers of 0. Fraction of 1s is 1/6. Fraction of zeros is 5/6. This comes out to be about 0.37. And expected value for 100 draws is 100 times 1/6, or 16.67, if you like, 16 2/3. And the standard error for the sum of draws is square root of 100 times 0.37, the SD of the box. So this gives us 3.7. OK? So in 100 die rolls, we expect to get about 16 2/3 sixes, give or take about 3.7. Right? So questions on that? OK, so I want to do one more quick, just talk through one more quick thing, and then I'll get to chapter 8 or 18. So to sort of summarize the kinds of boxes we've talked about. This isn't every kind of box that you'll encounter, but it's most of them. There could be sort of just pure numbers in the box, like die rolls. Or just a lot of problems in the book we'll just talk about, suppose you have these tickets in your box. Okay? So the numbers don't really have any kind of real world meaning. You have a lot of problems that deal with gambling problems where you're talking about net gain. The net gain is like the sum of a bunch of wins and losses. So the numbers on the tickets represent dollar amounts. Okay? And then the third thing I'll mention is this classifying and counting thing. So this is zeros and ones go on the boxes, go on the tickets. This is going to be pretty common as we move forward into doing data analysis. It's very common that you want to count something or think about the percentage of times something happens, like the percentage of times you get heads in real world examples. So we'll get into like polling where you think about the percentage of people that will vote a certain way or something like that. Okay, So that gives us a quick summary. One more thing I'll say, I guess, is that sometimes you'll find problems that are a little bit of a combination of these ideas, that you're dealing with something where you have to play with your box a little bit to get this idea that the numbers on the tickets represent what can happen to the quantity of interest on each time. Okay? So sometimes it'll seem like some kind of weird combination of these. But again, if you just think like, what can happen to the thing I'm interested in on each draw, that logic usually will get you through most problems. Okay, questions? Okay, so that's a little bit early for break, but let's take a break, and then this is end of chapter 17. I'll get into chapter 18. Okay. I just want a blanket for now. Okay, so going into chapter 18, I kind of want to give you a little bit of a transition from talking about histograms to probability histograms. Histograms are sometimes referred to as empirical histograms. Empirical just meaning that it's based on actual data. Okay, so you're actually doing something. So we've done that before, and I want to describe Karich's data. Remember, Karich is this guy that tossed a bunch of coins. And I want to think about his data in terms of empirical histograms. So first I'll just write his data down. So in 10 tosses, he got 4 heads. 100, he got 44. In 1,000, he got 502. And in 10,000, he got 5,067. Okay? So if we draw a histogram for his data, what I mean by that is to think about this as like a bunch of ones and zeros. So we have 10 data points, 4 of them are ones, and 6 of them are zeros. So if I want to draw a regular histogram for this, it's a discrete histogram, zeros and ones, and like I said, I'll think about it as, 6 of those, 4 of those. So I don't really want to mess too much with the, making the density scale and all that, but actually I'll do it, let's see. I'll say it this way. Okay? So it's a discrete histogram, so the width is 1 for each bar. So width times height gives us 60% for this first bar, 40% for this bar, meaning 40% ones, 60% zeros, 4 heads, 6 tails. Okay, any questions about that first one? Okay, so then for this one, what's it going to look like? It's going to be somewhat closer together, these two heights. So the first one is still higher. It's at 56. The other one's at 44. They're somewhat closer together for the second one. For the third one, so this is 10 tosses. This is 100 tosses. For 1,000 tosses, they're quite close, right? We have like 50.2 and 49.8. So just draw the second one just a little tiny bit taller. Okay, 50.2 compared to 49.8. Okay, and then finally this one is 50.67 versus it's 49.33. 50.67 is the height of the tall one. 49.33 is the height of the slightly shorter one. We have 50.67% heads and 49.33% tails. Okay? So what is the law? These are all what we would think of as regular histograms, empirical histograms. They represent actual data. It's kind of like a bunch of ones and zeros. Okay? What does the law of averages tell us about these pictures? What should happen as we increase the number of coin tosses? Sorry, I can't quite hear. Someone have a? I think it was right, but I didn't quite hear. Now everybody's shy. What's that? Yeah, it should sort of level out, right? The law of averages tells us in general that the percentage of heads should get closer and closer to 50%. As we increase the number of coin tosses, percentage of heads should get close to 50%, which means that we should be very close to getting the same thing for these. You can see that this is a little bit farther off, a little bit closer. As I said before, this is kind of unusually close. This is very, very close together here. And then this is still pretty close, although not quite as close as it was here. The general tendency is that as we get closer to 50% heads, these bars are almost the same height. Okay? So that thing that they're getting close to is called a probability histogram. So probability histogram represents chance by area. And it's generally done in percentage terms, meaning that just like that thing, if I extend that, if I think about that example, for one coin toss, if I draw a probability histogram for one coin toss, it looks like this. Okay, so these are actually the same height, 50%. So what this means is that each of these bars has area 50%, meaning that there's a 50% chance of that thing. 50% chance of tails, 50% chance of heads. So like I say, these empirical histograms, as you increase the number like sort of increase the amount of data, you're getting closer and closer to this probability histogram, right? So yeah, when I say generally in percent, this is sort of our standard definition of a histogram, that area is in percentage terms. Sometimes you'll see probability histograms where rather than thinking about thinking about chance in percentage terms, you'll see things like this. That just means, you know, this area still represents chance, but it's the usual way we think about chance. The area of this bar is 0.5, meaning the chance of tails is 0.5. The area of this bar is 0.5, meaning the chance of heads is 0.5. Okay, so you know, you can think about chance in either percentage terms or not. To be consistent with the regular histogram, the book will do it this way. But you know, the other thing is pretty common to think about the chance as a fraction. Okay, so the law of averages, like I say, says that those empirical histograms, as we increase the number of coin tosses, should get closer and closer to this. So over here, in chapters 3, 4, and 5, I talked about how if a histogram looks like the normal curve and we know the average and the SD, we can use the normal table, standard units, all that kind of stuff we learned in chapter 5. Similar sort of thing is happening here. If we know the expected value and standard error, and the probability histogram looks like the normal curve, we can do a bunch of normal table approximation stuff. And it'll look very much the same. We'll use standard units. We'll do a bunch of the same stuff. But this has to look like the normal curve, right? This doesn't, right? So for this case, with just one coin toss, we don't get the normal curve, okay? So part of what I want to develop today is, well, when does it look like the normal curve, all right? So there's some good pictures in your book. So I thought I'd show you some of those. So what do I want here? That. And thanks. So this is a picture that's in your book, and let's do that. Okay, cool. So this picture here represents 2 die rolls, okay? All the results are between 2 and 12. So I'll write a box model over here for this situation. So what we're talking about is, for the picture, we have our box 1, 2, 3, 4, 5, 6. So incidentally, for the other probability histogram, it's just one coin toss, 0, 1, 1 draw to get that other probability histogram. This is 2 draws from this box. So we're taking the sum of 2 die rolls. You can see all the results are between 2 and 12. This is an empirical histogram. This is not a probability histogram. This is a simulation, and again, this is in your book. It's page 311 if you want to look at it later. So what this is telling us is that in 100 repetitions of this, so we do this 100 times, there's some data. Okay? So we have 100 numbers. Some of them are 2s, some of them are 3s, some of them are 4s, not so many 5s, a bunch of 7s, you know. Okay? So that's sort of actual data. If you just made a list of all the results for taking 2 dice, recording the results 100 times, might look a little bit like that. Okay? All right. So that's like I say, 2 die rolls. This is also 2 die rolls, but we've increased the number of repetitions to 1,000. Okay? So we just got more data. We're doing the same thing, rolling 2 dice, but just more data. And you can kind of see that, you know, maybe there's a little bit of some kind of a pattern emerging here. Okay? So, you know, sort of kind of steps up and steps down again. Something's going on. If we go to 10,000 repetitions, we get something that looks like that. So there's some kind of shape or pattern coming together here. Now, if you think about Karacz's data, his example, we have the, you know, for 10 coin tosses, 100 coin tosses, 1,000, 10,000. We're getting closer and closer to this probability histogram, the 0, 1, even height thing. So doing this is sort of doing the same thing. We're always rolling 2 dice, just like Karatz is always tossing 1 coin at a time. Record the results, do it over and over again. These empirical histograms are getting closer and closer to a probability histogram. Okay, so here's the probability histogram. This hopefully looks like it has a very, very regular shape. Okay, so if you look at the one before it, it looks pretty regular, but if you look carefully, it's not quite evenly going up and down the way that this one is. So I don't know if you can see that in this picture, but it's not quite exactly symmetrical, and some of the some of the steps are different sizes. On the bottom one, it turns out that each of those steps is exactly the same size. Same size. So for example, I could there should be like a straight line here, because those steps are exactly the same size, and a straight line going down. All the steps are exactly the same size. Okay? Here, it doesn't quite work. There's like little, oops. I don't know, it might look like it does. But it shouldn't. It shouldn't quite be exact. Okay? So if you look at this one, you know, they're not quite perfect steps the way the last one is. Okay? Or they shouldn't be. They're allowed to vary a little bit. Certainly the one before, the steps are kind of irregular. 10,000 repetitions is a lot, so it does look quite close to the probability histogram, but it shouldn't quite, you know, it's not exact. Law of averages tells us, the law of averages here is sort of interesting. It works in every bar simultaneously. So the law of averages tells us that if we do this, roll 2 dice over and over again, in the long run, the area of any particular bar should get closer and closer to the area of the corresponding bar in the probability histogram. So like the proportion of 9s in 10,000 repetitions should be very close to the probability of 9 in the probability histogram. Okay? So this is, you think about this as being each bar represents a proportion. In the last one, each bar represents an actual probability, right? Okay, so maybe I'll calculate one of those just for fun. Let's find the probability of getting a 10. Okay, so probability of 10. If we think about, you know, drawing a grid, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 6, 4, 5, 5, or 4, 6 gives us 3 out of 36, which is 1/12. As a probability, that's 8.33%. Okay, so let's see if we believe that. There's a bar over 10. Actually, the bar over this 4 is the same, so maybe I'll look at the bar over 4. 4 would be 3, 1, 2, 2, 1, 3. Same chance. It's a little bit easier to sort of go over here and see that this bar over 4, if we kind of follow that along over there, it's a little bit less than 10. Height's a little bit less than 10. Kind of should be believable that that third bar over has an area of 8.33 anyway. Okay? So that's what's literally going on, is that last picture, no dice were actually rolled. It's all based on this kind of calculation of what the chances should be. And you can see why it steps up in instead of an even way from this. 1, 1 has 1 out of 36 chance. Getting a 3 has a 2 out of 36, then 3 out of 36, 4 out of 36, 5 out of 36, 6 out of 36, and then it goes back down again. 5 out of 36, 4 out of 36, steps back down. 12 is 1 out of 36, the very last bar. Okay? So yeah, the probability histogram has that shape. This still does not really look like the normal curve, right? It sort of doesn't have this nice curvy bell shape. It's maybe a little bit closer. It's at least taller in the center. But here, I wouldn't want to use the normal curve. I wouldn't want to use the normal table to figure out areas here, right? I would do it just by, if I want to figure out the area or the chance of any particular outcome for that, I just calculate it. There's no real point in using the normal curve to do it. Okay, but next example I do will actually use the normal table. All right, so the lesson I want to emphasize in these pictures is that as we increase the number of repetitions, we get closer and closer to that probability histogram. The empirical histograms get closer to the probability histogram, and the reason is basically the law of averages. The law of averages is telling us that the area, let's go back to this top one that's all funny looking. The area for the bar over 4, for example, that area of that bar should get closer and closer to 8.33, the actual probability. You can see it's pretty far off there and maybe pretty close for those. And for every bar that's going on, these bars in the beginning may be pretty far off because it's not very many repetitions. As we get more repetitions, we should get closer to the probability histogram. Okay, questions? Okay, so that's one lesson, that empirical histograms get closer to the probability histogram. The next lesson is to actually think about the normal curve. So I'll draw this, I'll just put this picture up here, first of all. This is coin tosses. Okay, so this is the situation I've calculated for. 100 coin tosses, expected value is 50, that's right in the middle. Standard error is 5. So you can look at the standard units axis and see that one standard error above the expected value is 55. If you want to think about that the other way, if we convert 55 into standard units, we would take 55 minus 50 divided by the standard error of 5 would give us 1. Okay? So you can sort of see what's going on there in that picture. And the bars themselves, the sort of flat top rectangular bars, those represent kind of the truth. The area of that bar is just like in that other probability histogram. This is a probability histogram, right? Everything I'll show you from now on is a probability histogram. It's not empirical. It's based on the actual chances. So the bars, each bar represents the chance of that particular outcome. Okay? There's a normal curve superimposed over it to illustrate that, in fact, this probability histogram does look like the normal curve. The other ones we looked at didn't, right? We have this 0, 1 thing with just like 2 bars, flat, doesn't look like the normal curve. For 2 die rolls, it's maybe a tent shape or something like that. It's like not so bell-shaped. The normal curve follows this probability histogram quite well. So if we, for example, wanted to find the chance of getting, between 45 and 55 heads, one way to do it would be to calculate the area of each of those bars separately. You could do it using binomial formula, okay, and I'll show you that calculation in a minute. You could do it, but it'd be kind of a pain. If I made you do it for homework or something, find the chance of 45 to 55 heads, you'd have to do each bar separately, add them all up. It'd be kind of a drag, okay? If we could say that that chance is about the same as the area under the normal curve between 2 numbers, maybe that's easier, maybe that's faster, okay? So I'll do that. So before I do that, let me just, while I have this up here, I'll show you some more pictures. So this is for 100 coin tosses. Looks pretty good. Looks a lot like the normal curve, right? Well, 400 coin tosses, even better. This is those. There still are bars, right? There's really skinny bars, and the normal curve is following the bars pretty well. There are like little edges of the bars that poke outside and a little bit inside. 900 coin tosses, is almost indistinguishable from the normal curve. So there are still like little tiny edges poking out and stuff, but there really are bars there, right? There's a bar over 450 in the very center, little skinny bar. Again, the area of that bar represents the chance of that particular outcome. Follows the normal curve quite well. While I've got these up here, I want to mention one other thing, which is part of the law of averages. Law of averages says that as we increase the number of draws, we should get larger chance error in absolute terms, smaller in percentage terms, right? So you can kind of see that 1 SD away is 5 off for 100 coin tosses. It's 10 off for 400. It's 15 off for 900. Okay? So the standard error is getting bigger as we increase the number of tosses. That tells us that the sort of absolute or raw chance error is getting bigger, tending to get bigger. If you think about it in percentage terms, it's a little bit hard to see, but in percentage terms, we're getting closer. So one standard error away here is 55%. That's 5% off. One standard error here in 400 coin tosses, this is 210 out of 400 is 52.5. So this is off by 2.5%. Okay? So one SE above the expected value here is 2.5%. Here it's 5%. So that sort of is an illustration that in percentage terms we're getting closer. Okay? One final point about the law of averages is that there's a part of the law of averages that says that the chance of getting exactly the expected value, exactly 50% heads in this case, that chance should get smaller. Well, to get exactly 50% heads, we need to get in the bar that's in the very center. The area of that bar in the very center gets smaller. Just think about it as a raw area. These bars are skinnier. They have less area, right? So the chance of getting exactly 50 heads, or exactly 50% heads, is getting smaller as we increase the number of draws, because that's just the one bar that's in the center. Okay, any questions about this before I take it away? Okay, so kind of have this first picture in your mind. I'll draw a quick sketch of it, and I want to calculate some probabilities off of it. So, okay? Any questions before I get rid of it? Okay. All right, so let's use that board over there. So I'm going to do 100 coin tosses again. I want to find the chance of getting exactly 50 heads. So first I'll do it the binomial way. So remember, the binomial tells us if we have independent trials. So these little, like the coin tosses are like trials, each with the same probability of success. P is 1/2 in this case. We can use the binomial formula to find the chance of exactly some number of heads. So basically, in this context, we have N is 100 trials, P is 1/2, the chance of getting heads, and K is the specific thing that we want, exactly 50 heads. Okay? So probability of K, meaning 50 heads in 100 tosses, is going to be 100 factorial over 50 factorial. This is n factorial divided by k factorial, n minus k factorial, 100 minus 50, and then 1/2 to the 50th, and 1 minus 1/2 to the 100 minus 50. Okay? So I'm doing it sort of strictly by how the formula is. Obviously, 1 minus 1/2 is 1/2, so I could actually group all these together and just say this is 1/2 to the 100th power, if you want. Anyway, this is, if you actually calculate it, 7.9656%. say is. Really, this is a decimal, so it's kind of not true if I say equals. It's equal to 0.079656. But I want to write it in percentage terms. OK? So that's that. And that's sort of the right answer. That's the actual area of the bar. If you imagine our picture, you have some bar in the center over 50. And then bars next door at 49 and 51, so forth. OK? So that's the actual area of that bar is 7.9656%. OK, so it's approximately the same as the area under the normal curve. So that top picture I'll just do a quick sketch of. The top picture from the slide. We have a bar where 50 follows the normal curve pretty closely. And basically, what I want to do is this. I want to convert into standard units. What is it that I should be converting into standard units? What value? So from previous calculations, I know expected value is 50, standard error is 5. I won't calculate that again, but it's the same box model. Do I still have it up? No, I erased it. So yeah, expected value is 50, SE is 5. So we're going to take a value, subtract off the expected value, divide by the standard error. That's going to give us standard units. So in this context, we take a value minus expected value divided by standard error. This is just analogous or similar to what we would do with average and standard deviation. What's the value I'm going to use here? Any thoughts? Someone said 50. What will happen if I do 50? I'm going to get 0. So what I'd like to do is I'd like to approximate the area of this bar. The center of that bar is at 50. The center of the next bar is at 51. Any thoughts? Yeah. 50.5. Yeah, so what I want to do is I want to find the sort of best answer I can get from the normal curve is going to be the area under the curve corresponding to those edges of the bar, right? So if I can find the area between the left edge of that bar and the right edge of that bar, that's what I want. So this right point is going to be 50.5 minus the expected value divided by the standard error. That comes out to be 0.1. 0.5 over 5 is 0.1. And the left edge is 49.5 minus 50 over 5. It's minus 0.1. Okay, so the normal, using the normal curve in this context is a little bit different than what we did before when we were talking about data. For data, we generally are assuming that the data is continuous. So we're using the normal curve as a way of approximating a continuous histogram. This is discrete, so they're discrete whole number values here. The bars are centered on the values. So if I want to find the area of that one bar in the middle, it's going to be about the same as the area under the curve from there to there. Okay? So this answer I'm getting is the area under the curve between 0.1 and minus 0.1. And that's, if you look that up, that's about 7.97%. Okay, that's off the normal table. Right? If you look at 0.1, you get that. So it's quite close, right? It's very, very accurate. The normal approximation answer is just a little bit bigger than the answer you would get from actually doing binomial. So the truth, the right answer, is the area of the bar, right? The area of the bar truly gives us the chance of getting 50 heads and 100 coin tosses. It's approximately the same as what is going on with the normal curve. So that's why it's called normal approximation. It's excuse me, approximation of the area of a bar or a bunch of bars for the probability histogram. Okay, any questions on that? Okay, so I want to do sorry, lost here. There we go. Okay. I want to do another one from this, the one I sort of said in words, the chance of getting 45 to 55. So still 100 coin tosses. So the book has this word inclusive. Inclusive means including the endpoints. If I just said find the chance of 45 to 55 heads, it's a little bit vague as to whether or not 45 and 55 should be included in that calculation. What's really going on, right? Excuse me. What's really going on is I have a bunch of bars. 1, 2, 3, 4, 5, 55. 9, 8, 7, 6, 5. 45. So if I say 45 to 55 heads, well, there are a bunch of bars, and the problem is if I don't say the word inclusive, it's unclear if I want, it's unclear exactly which bars I want, right? I might want the bars from 46 to 54, or I might want to include the bars over 45, 55. A little bit vague, okay? So I'll talk a little bit about this on Thursday, I think. I don't think I'll have time today, but that issue of like, you know, including the bars or not. This includes the bars. So when you think about the area then, I want the area from the far left to the far right, okay? Now, again, the right answer I could find using binomial. I could figure out the probability of each of these bars individually, basically doing this, right? The chance of 45 would be 100 factorial over 45 factorial, 55 factorial, 1/2 to the 45, 1/2 to the 55, okay? So I could do all that. I could do it for every bar separately, add them all up. I'd get the right answer. And I did that. And the area of the bars from the binomial is 72.8747%. Okay? 72.8747%. So like I said, that's sort of the truth. That's the right answer. That's the sum of all those bars. Doing normal approximation, I want to find those two edges, right? The edge of the far left bar, the edge of the far right bar, converting to standard units. So I'll do the far left one first. What should I use? For the what do I want to use for my value? 44.5, right? That's the left edge of that leftmost bar, right? Subtract off the average, subtract off the expected value, divide by the SE, and this gives minus 1.1. And for the far right side, 55.5 is the edge of the far right bar, minus 50 over 5 is plus 1.1. Oops. So if I look that up on the table, I get an area of, where is it? I got caught without a normal table. Is it 72.87? Does anyone have a normal table? Yeah, 72.87, okay. Okay. So, you know, if you just round that, you get the same thing, right? So this is very accurate. Even for 100 coin tosses, it's very accurate. As we have even more coin tosses, like in those pictures, if we do 400 coin tosses, 900 coin tosses, it gets even more accurate, okay? So question you might ask at this point is sort of, you know, when is it okay? I sort of started out by saying, you shouldn't do it here, right? This does not look like the normal curve. If you sort of tried to superimpose a normal curve here and find the area of one of these bars based on the curve, it's not going to do so well, okay? So when does it do well? I'll say this sort of generally first. As the number of draws from a box increases, the probability histogram for the sum of draws looks more and more like the normal curve. Okay. I think that should be surprising. If you understand what this sentence means, I think that should be surprising. It doesn't matter what the box is, okay? I could start with a box like this case is just a 0, 1. I could do it for die rolls. I could do it for the roulette problem, whatever. It doesn't matter what box you start with. If you have a large number of draws, the probability histogram for the sum of draws will end up looking like the normal curve. Doesn't matter what you start with, okay? So this is what's called the central limit theorem. Proves this. I don't usually quote theorems so much in here. This is sort of a biggie. I don't really care if you know the name of this. I would like you to know that there is a theorem which says essentially this, basically saying it doesn't matter what you start with, doesn't matter what the box looks like. If you increase the number of draws and look at the probability histogram for the sum of draws, it'll eventually look like the normal curve. Now, it might take a while. It might take a pretty large number of draws, depending on what you start with. If you start with something that's sort of, relatively symmetrical, like coin tosses or die rolls, pretty nice, it happens fairly fast, actually, that you'll get a probability histogram that looks like the normal curve. You can see even with 2 die rolls, it's starting to look like something kind of vaguely normal, right? If we just look at 1 die roll, we just get this flat 1, 2, 3, 4, 5, 6 flat histogram. 2 die rolls, you get this tent. 3, 4, 5 die rolls, you start getting a little bit of a curvy bell shape. Yeah, so anyway, this is for 100 coin tosses. It does very well. In my example, the bars look a lot like the normal curve. If you start with something fairly weird, and I'll do an example of this on Thursday. If you start with something fairly weird, it won't look like the normal curve until the number of draws is quite large. Okay, you may need more draws. I'll give you a little rule of thumb. So for exam purposes, 2 things. At least 25 draws. And second, if you go 2 standard errors each way from the expected values, this should be in range of possible values. So let me describe what I mean by that. Sorry, I'm getting sort of small again in my writing. Expected value plus or minus 2 standard errors is in range of possible values. So you want to check both of these things. You need to have at least 25 draws, and this needs to be true. So let's just quickly go through my example here. With 100 coin tosses, expected value is 50, standard error is 5. If I go 2 standard errors to the left, that's 40. That's within the range of possible values. 2 SEs to the left would be 60. That's in the range of possible values. Range of possible values here is anything from 0 to 100. I could get anywhere from 0 to 100 heads. So let's suppose that somehow the standard error is 30. Expected value 50, standard error 30. If I go 2 standard errors to the left, I get negative 10. That's not in the range of possible values. What that's telling us is that there's something wrong in the sense that the normal curve ought to have area 200, like 2 SEs away, right? 95% of the area is within 2 SEs. There ought to be a little bit of stuff to the left of 2 SEs below the expected value if it really does look like the normal curve. So if you go 2 SEs to the left and there's nothing there, you're out in this area where there's no probability histogram, you're past all the bars, the normal curve would tell you there should be something there. If there isn't, well then the normal curve must be wrong. The probability histogram, remember, is the truth. So wherever there are bars for the probability histogram, that's where there's really some chance, right? So that's why this second one is useful. This sort of takes care of cases where you have something that's very skewed, long right tail, long left tail. In general, 25 draws is usually pretty good, but sometimes it'll fail. So that's why I'm tacking on that last one. OK, so I guess I'll stop there. That's a pretty good stopping place. A little early, but OK, so I'll finish up chapter 18 on Thursday and get in chapter 20. And then break.